Today is, guess what? Last lecture. So this is it. This is it. Is this what you've been looking for? Yes. Yeah, so I know what you're looking for, and I have something very surprising at the end of my lecture, something that you couldn't believe your eyes. So we'll see. So exciting lecture, lecture number 12, last lecture of this entire course. And today we're going to discuss about something pleasant. So we're going to discuss about where exactly we can use the knowledge we have learned. Of course, you get a little bit an idea about that in introduction part. But today we're going to take a deeper look, like what exactly is that we can use this information you learned about multi-body system dynamics and simulation of a mechatronic machine. So that's going to be a subject matter of today's lecture. We shortly going to take a look at the game technology businesses as well. And then the main body of today's lecture is going to be recap, so summary. What is that I'm expecting you to know in next midterm exam, and then what? Then we're going to close it. That's it. So we'll see how it goes. And let me see how are the online participants. I think yeah, there was a problem that the streaming died a little while ago, and that was because my connection was I connected my laptop to incorrect Wi-Fi, but I think it is now okay. All right. So with that, let's first look a little bit about what we discussed a week ago, and then I have a couple more slides about deformable bodies. I'm not planning to spend too much time about the deformable bodies, but the short highlights about that subject matter, and we will get back to that. I mean, those of you that will assign to this simulation laboratory course, we will discuss more about how is it we can combine different softwares together, like finite element method software that is capable to model control schemes and so on and so forth. So that's going to be another course then. But flexible bodies. And remember that the need to model deformable bodies is because we would like to make more accurate models. So we would like to make a better representation of reality. And sometimes, particularly in a hydraulically driven structures, they are somewhat slender structures and they are flexible structures. And the flexibility is so significant that to make realistic predictions about the reality, the flexibility needs to be accounted. And there are several ways you can do it. And a week ago we discussed about the method that is very rough method, is this lamp mass approach. There's actually even kind of the simple method than the lamp mass approach, and is have a really fancy name. It's called linear theory of elastodynamics. That is a method where we are assuming the body to be initially rigid. And then we take a look at all the forces that is imposed to body. And those forces are then used as a pre-processing or post-processing procedure to compute how much deformation those forces are capable to introduce. And then this deformation that can be computed using finite element approach, or it can be just these analytical equations that will be superimposed to rigid body motion. So that's something that is very coarse method and is not used heavily. Well, at the moment is not being used almost at all because it's theoretically incorrect way to do it. And that can lead to seriously incorrect responses. So it's a risky business to use something like that. Anyways, lamp mass approach is a simple approach where we take an original rigid body and we're going to divide the original rigid body to number of rigid bodies. And what we're going to do then is that we're going to add the spring elements between these rigid bodies such the way that there is a stiffness to each of the 6 degrees of freedom in spatial case. And that's all that is needed. All that is needed. And that's about it. And here are the few examples where it's being used. And these are really old videos. They are like more than 20 years old videos. And they've been used to model beam-like bodies. You see that this beam here is modeled as a flexible structure. And here's a hydraulic driven crane where the lift arm and swing arm are modeled as a flexible bodies, and that's all based on the lamp mass approach. So it can be used in applications like this, but it is not advised to use it at the moment because it leads to situation where the computational efficiency is not very good. And this is simply because of this numerical stiffness. Remember that this situation where you have low frequencies and very high frequencies simultaneously. Integrators, the numerical time integration schemes, they can recognize the low frequencies, of course, but they recognize the high frequencies too. And they usually adapt themselves due to or based on these high frequencies. And that slows down the computation very significantly. And the method can be applied to beam-like structures. There are studies that this lamp mass approach is being used in plate-like structures too, but it becomes to be cumbersome to do so. Not so straightforward anymore. And material damping model is simple. I don't think that's a serious problem, but that is something that is good to take into account. Easy to implement, easy to use, because theory is based on rigid bodies. And that's it. That's about it. Okay, then a short few words about alternatives, which is currently dominating method to model flexibilities. It's a great method, but it's unable to describe very large deformation because in this method, the strain displacement relationship, what we discussed a week ago, it is assumed to be linear. Well, in many cases that's okay, so it's not a big deal, but good to keep in mind that this is not capable to describe large deformation, like in the case of belts. Just cannot do it. Okay, what is this method then? It is called the floating frame of reference formulation. Very lengthy, complicated name. What that means, essentially, is that we're going to use this body reference coordinate system you guys are familiar with. And we're going to introduce finite element method with respect to this body reference coordinate system. That means that deformation computed based on finite element method is not tried to describe these large translation and rotations that are already described by using this reference coordinate system, but small deformation with respect to reference coordinate system. And this reference coordinate system, that's the one that is called floating frame of reference. The floating is a special case that can be every now and then something that you need to consider. But it means that this reference coordinate system is traveling, translating and rotating, but it can be attached to the body in a way that it is not attached the similar way that in the rigid bodies. Because in rigid bodies, there is no relative motion. Whereas in a flexible bodies, there can be a little bit of relative motion due to the deformation. That's where the floating term is coming from. Anyways, idea here is very simple. So we take a reference coordinate system, which is the body coordinate system we used to deal with, and we're describing the deformation with respect to that coordinate system. It looks like this. So in a three-dimensional space, we have this reference coordinate system, and then we have original location where the particle is located at in undeformed configuration. And then there is a deformation, which we do not know how much is a deformation, which here is described by using vector u bar f, this guy here. And now we're going to simply change the kinematics. Are we adding one component to our very well-known kinematics? Remember, in rigid bodies, it went such that it was r plus a, this is a rotation matrix multiplied by vector u bar. And now what we're going to do is that we're adding something to this vector u bar. Now we're adding something in a way that we're going to take the original location or original position of the particle into account, and then we're adding deformation on it, like this. This deformation, this guy here, will be computed using the finite element method, which is a method very heavily used in a structural strength analysis. Finite element method is a method where we are discretizing our original structure by number of elements, which is approximate about the final solution. But once we keep on adding those elements, we can get an approximate that is very, very good. These elements are connected together in nodes. And that's basically what the finite element method is about. Now these nodes, we can use to compute the deformation. And that is represented by using this vector u bar f in the floating frame reference formulas. Okay, let me just continue. So, generally speaking, here's the situation. We have multi-body system dynamics that is taking care of the large translation, large rotation. How it can take care of that? Well, with help of this reference coordinate system, that one here. And then we have a finite element method that is taking care of the small deformation with respect to that reference coordinate system, the one that is already traveling, translating, and rotating. We combining them in one package, and that's where you can get this floating frame reference formulation. That, in short, that's how it goes. There is, however, a big problem that we still need to do something for that big problem. And the problem is such that if you think about number of unknowns in the case of multi-body system dynamics. So in one spatial body, we need 6 or 7 coordinates. Let's say that we need 6 coordinates. Whereas in a finite element method, it's very common to see models that consist of 100,000 degrees of freedom, 1 million degrees of freedom, meaning that this one here that is used in a finite element method, this number of nodes and nodal degrees of freedom, that is easily very high. So high that things are not matching well. You know, think about 100,000 versus 6. They are not in the same wall, so they are not comparable. So we need to do something to this guy, finite element model. Something we can do for the finite element model is that we can make it smaller. And that's something that is called modal reduction, or the one way to do it is called modal reduction technique. Let me just see what is a comment. So there is a complaint about my mic, that you don't see me, you don't hear me well. Okay, so is it getting better? So this is what I'm asking for online participants. Is it better? Okay, now better. Okay, very good. So I gotta keep it like this. Sound is okay. Very good. So I was about to say that we need to do something for that finite element model. And something that we can do for that is that we can reduce the size. Okay, this is a little bit of a lengthy story, and I'm going to cut the corners, but basically what we do with this finite element model is that we're going to take a look at the possible deformation, how the entire structure, this time entire body, can deform. Okay, it can deform as many times that there is a number of nodal degrees of freedom. So meaning 100,000 times if you have that size of the model. Some of them, these deformation modes, are important, whereas some of them are less important. And what we're doing then is that we're going to take a look at these possible deformation modes, and we're selecting the ones we feel are the most significant ones, ignoring the rest. And ignoring the rest is a lot. So again, taking you back to the model where there's 100,000 degrees of freedom, typically we can use 10 modes, 10 deformation modes. So we really are reducing the model size. And that's what makes it possible to use it as a part of the multi-body system dynamics. So this is how it works then. So this is this lower limb model that we looked in the first lecture. There is a tibia and femur bones are modeled as a flexible bodies. because we wanted to study the strain and strain rates in both the lower body. And it was based on this kind of deformation modes. These were the deformation modes, excuse me, that we select to be representative of this kind of motion. This is a human tibia bone, and it was made by using MRI and CT, so computer tomography and MRI. And based on that information, it was patient-specific model. So this was really representing somebody's bone. And then these are the deformation modes that were used in that particular example. More example is here. So these are the structure which is come from hydraulically driven crane. These are the lower deformation modes that are most probably very important. And then just to give you an idea, what are the high deformation modes is this. This you can ignore. You don't need to worry about that because that will make an insignificant contribution to final response. And that's what the model reduction technique is about. Okay, so with that, I'm going to move on to real-time simulation and games, if no comments, questions. Meaning no comments. Okay. All right, so let me see. Okay, the online participants are saying loud and clear, so that's very good. Okay, so again, what's going to happen today? We're going to spend a little bit of time about this real-time simulation and games. And then we're moving on to summary. Information I'm expecting you to master in second midterm exam. We need to make an agreement when to organize it. And I checked the calendar, and I was saying initially that exam will be in a week 51, which is not a good week because that is a Christmas week. And that's going to be, at least those ones that are spending Christmas, it's going to be inconvenient to do exam in 24th or 25th of December. That can lead to consequences in your family life. So that's why I'm proposing not to have it in that week, but in week 50 and in week 49. But we get back to that. So there's going to be 2 weeks time that the exam is open, and you will have 2 attempts. Sounds okay. Anyone wanted to do it in a Christmas week? So that many wanted to do it in a Christmas week. Okay, so okay, no Christmas week. Okay, I got it. All right, so background. Okay, I want to play your video. I don't know how well it goes to you. Let's see.
The Laboratory of Computational Mechanics.
No voice. Where the voice goes.
That is advancing real-time simulation for mobile.
I guess it goes to online participants. Okay, let me take it. Let me start this again. Oh, it should go here. Why is not doing that?
The Laboratory of Computational Mechanics is a mechanical engineering research group at Lute University that is advancing real-time simulation for mobile working machinery.
You don't
A
see
particularly important focus of the work.
Okay, let me try to do this one more time. Maybe I can play this video to you because not no, not that. Not that. No, you don't see that yet, but you will see it momentarily. No, it comes without the voice. So this was introducing a little bit of research we do in the laboratory of computational dynamics. By the way, our official name is not computational dynamics, but machine design. And the machine design is something that is implying that we do some kind of artistic work in a team, that we don't do. It's because of the language conflict between the Finnish and English language. So we don't really do any kind of artistic things. Look at me, and that becomes soon very clear that no talent in that direction. But what we do then, instead of that, is, and you don't even see that. You don't see at all. Okay, what happened then? So it was displaying something to you, but what was it then? Okay, let me do it one more time. P. Oh, it was extending the screen.
The Laboratory of Computational Mechanics is a mechanical engineering research group at Lute University that is advancing real-time simulation for mobile working machinery.
Yeah, I don't know if the voice goes to online participants, but
Development of better digital twins, which are virtual representations of machine systems.
I got the warning message to my YouTube which says that the connection is poor.
Is an important aspect.
Very big disappointment because there was a big surprise to you at the end of the class, and maybe now I need to skip that big surprise. Okay, we'll see. Okay, but anyway, so this is just showing what are the research activities we do and what kind of different real-time simulation models we're playing with. And the real-time simulation, generally speaking, is exactly what you learned in this class. The only difference is that the solution you do in the real time is that you're synchronizing the solution to actual time. And that means that you need to make implementation, computer implementation such that you make sure that all the computation can be carried out within the certain time limit. And once you are able to do it, then you can synchronize your simulation to real time. And that's a little bit of an example what the games are and what the games are capable to do. Sorry that this video is not available, and I also got this connection problem message in my YouTube studio, so hopefully it's not too severe. But anyways, so that was a short introduction about the real time, and this is showing thematically what it means. Okay. So in a real-time simulation, we are making the representation of mechanical components. Those will be based on multi-body system dynamics. What we also gonna make a representation of actuators. Very often they are hydraulical actuators, but they could be something else too. And then control system is somehow involved with, and the working process too. And then we're gonna take a user as a real person. We can ask person to operate these models in a way that we're solving these computational aspects. Oh, you don't see my drawings now, but this working process, mechanics, actuators, and the control system, such the way that every single computer needs to be carried out to predict the dynamics can be made in a predefined time frame. And this time frame needs to be shorter than actual time. We do the computing, we read the signals from the joystick or whatever is the means that we're operating the machine, and then we behaving accordingly. So according to based on the signal from the user. So there is a real user typically involved with, but not all the cases. There could be the cases that the user is replaced by artificial intelligence, and that could be okay too. And in that case, we can teach, we can learn to use a machine by using some kind of learning techniques, or we can use a predictive simulation, which I will get back to that to you. So that's the big picture. That's how it works. And here's another animation. I'm pretty sure that the voice is not, let me just make sure that the voice is completely off. So they are like real-time simulation can be something that is shown here. So it could be a representation of entire excavator, meaning that mechanical components are described, hydraulics is described, contact between the ground and the bucket, contact between the different bodies of the excavator is described. And there's then also ground can be deformable, such the way that you can take a piece of dirt and you can move the piece of dirt from one location to another. Everything here, this mechanical modeling, also partly modeling of deformable ground is based on multi-body system dynamics. And you know that the modeling of hydraulics is based on land fluid theory. So you have a knowledge about each of these details needed to build this kind of a model. So it's not overly complicated for you guys. Okay, here's one video which shows how is when we put this in a Unity environment. Unity, those of you that are very much into the game technology, there are two platforms that are heavily used to build the games, Unity and Unreal Engine. So what we do is we're using Unity and Unreal Engine too, but not so much. But we make some trials to use Unreal Engine to describe or to visualize the engine. Engine itself is based on the technology which is a multi-body system dynamics. So that's is used to solve the physics-based performance, physics-based behavior. You know that there's something that is called game engine. They too are becoming to be more realistic all the time. And some of the game engines becomes to be they're fairly close to reality, but they still lacking certain features we need, like description of hydraulics. Sometimes the contact description is not accurate enough what we want. Sometimes we wanted to describe mechanical deformation in the bodies. That too is missing in a game engine. But generally speaking, game engines are becoming better and better all the time. Some of them are free to use. There are open source game engines that are very good already, very much advanced. Okay, so that's about that thing. Now what I would like to do is that I would like to give you highlights about where this real-time simulation can be used in different product processes. And I'm not going to explain all these possibilities it can be used, but I'm going to just give you a few highlights. And is it so, by the way, that you guys, now when I realize this, is it so that each of you participated the course that is organized by Tuhin? Each of you. So you know the story already. Because what I'm about to tell is more or less what I mentioned in a Tuhin's course about, what is it? Mechanical engineering something. So you guys are aware of this, or more or less you are aware of this. Okay, let me give you highlights and then we can discuss. This for sure will not happen, but let me have a dream in my mind. Okay? How is, by the way, everything so far? Is it everything clear? Any comments about how to model flexible bodies? Any comments about real-time simulation? It's all clear. Yes, yes, sir. Okay, so the question is like how close this is to reality. Okay, so that's a very good question. You know, to answer that, I need to take you back in a history. The time that happens already a while ago, the time that I was young, that time. You can imagine how was it. So it was a really quite a while ago. And at that time, there was a very heavy skepticism, criticism against dynamic simulation. And many people claim that what you can get out of the simulation is not according to reality. So there must be major differences between the reality and simulation model. And at that time, it was very common that each of the simulation model was verified against measurements. So what was the case that you built the simulation model of, let's say, an hydraulically driven crane or excavator, and then you went to the real machine, you instrumented the real machine with different kind of sensors, pressure sensors, position sensors, velocity sensors, and so on and so forth, maybe strain gauge as well. And then you operated the crane. You also recorded the signal that went to the direction valves. You took these signals as they were, you put them in a simulation model, and then you look how far they are from each other. And people don't do that anymore. And because well, after doing that a little while, it became clear that if there was a difference between the measured signal and the simulation model, most often the guilty was not the simulation model, but incorrectly made measurements. So they don't do that so often anymore. There was a couple, let's say 5, maybe 10 years ago, the same kind of criticism was against real-time simulation. And the same story again, like how can it can be accurate because you're computing everything in real time. So there must be some wrongdoing there. And again, they were measured or they were verified using measurements. And again, they accurate well. And after doing this a little while, what was left aside was a measurement. Thank you. Okay, so as this is all clear to you, I'm gonna just browse it over. So I'm not gonna look at the details, but just showing you the big picture. You know, there's a real-time simulation model because they are accurate representation of reality. They can be used in the product development and build a better understanding what is it the customers wants, what are their needs. This is like kind of like a traditional product development, but with the possibility to get the immediate feedback from the customers, which is a great benefit because otherwise you need to build the machine, you need to do it. And the world is full of these examples that the engineers made the real products and the customers hate it big time. They hate it a lot. And that's simply because there were no opportunities to get the feedback early enough. Some of the cars, people don't like them. They may be unreliable and so on and so forth. And that's because companies didn't have a mechanism to get the feedback early enough. Okay, so you can do that by using these real-time simulation models, and you can build a bridge between the product development and the customer. That's what you learned from my previous presentation. We've ingested that in a game environment where you can modify the model, like you can modify the model in a game. So you can tune your rally car, you can make it better. And the same way you can tune the excavator, you can select the different kind of hydraulic features and see whether or not this is something you like. By the way, I think there was something that I wanted to go back in the beginning. Oh, this was just like how is a trend? Like trend is about user feelings, expected user experience. User training models are the ones that are made already more than 20 years ago. And this was the standard policy 20 years back. Still real-time models, but not, of course, not as accurate that you can find today. These kind of models. User training is a special feature or a special case in real-time simulation because that you do not need to get that accurate physics. Sometimes kinematics is enough because you want to learn how the different joystick operation will move your machine. So you don't need to get that accurate dynamics in the case of user training, but the kinematics often will do it. Fault diagnosis, so you can build the different kind of failure maps. So what happens if there's a failure, different kind, and how the machine behaves in a case like that. That's possible with real-time simulation model. And it is possible to do something that Suraj guy, is doing at the moment. So he is doing something that is called reality-driven simulation. Reality-driven simulation is fixing the problem that you always have when you have a simulation model. And the problem is such that reality and simulation model never can be one-to-one match. Just that is not just possible because minor differences will be accumulating when you're simulating. Because these accumulated errors, the difference between the reality and simulation model becomes to be bigger and bigger and bigger until these two things has nothing to do with each other anymore. In reality-driven simulation, you force in your simulation to follow the measured signal that is coming from the real machine. Why? Because then we can get the estimation about the forces, about the loads, and so on and so forth. We can even get an estimation about the strains and stresses within the structure, even when we are not directly measuring, but computationally estimating. That's how it goes. Okay, and this is an example how it works. So we can have a real machine, and then the real machine is or there's a simulation model that is synchronized the real machine, and then they behave accordingly. And then we can dive into the machine, and we can measure the quantities that estimate the quantities that are not measured. That's the right way to put it. And this system level optimization, that's going to be my last second last example. This is this technique that you can compute faster than in real time. And when you're computing faster than in real time, you kind of have an ability to see what happens in the future. And when you have an ability to see what happens in the future, then you can tune your motions and your actions in a way that you can get something that it would be otherwise too difficult to get. This is my favorite, this driving a car. This car is driving across the heavy traffic. And it's not very good, so it's not very successful. Whereas when you have this ability to see in what happens in the future, I'm sorry I cut this in an incorrect place. You can, I think it is this place. Sorry that we need to take a look at this again. Yeah, this is a prediction. So it happens, it sees the different consequences. And because this ability to see what happens in the future, you can adapt your motion accordingly. This is a pendulum that is kept in upright position using this technique. So you see what could happen next, and you're tuning your system based on that information. And then this is an excavator that is, we use the reinforcement learning to teach how to operate it. It needs an awful lot of teaching. It's not very clever and needs an awful lot of data. How much data? This is a good example as this pendulum where there's a 4 bodies in upright position to explain or teach the control scheme how to behave. This required 1 billion analyses. So that's a lot of analysis. All right, so with that, we're gonna close the case. I don't wanna go this direction, but I wanna go here. Safety studies. So we also have these biomechanical models we can use in different scenarios. We can put the human to climb in the stairs and see if this is a too risky business. If there's a possibility to hit the head or something, that's all we can do. So that is a highlight about the work we do in laboratory of computational dynamics, which in Finnish is a laboratory of machine design. But we don't do design. We don't do artistic things. We do product development, but no artistic aspects. Okay, so I have another set of slides, which is a summary, and then we're gonna close. How that sounds? What? Sounds good. Okay, I got no comments from online participants, so just a second, I'm gonna take these away. Change my presentation to be this one. And of course, you don't see it, but you will see that momentarily. Okay, I lost the picture here. Oh, here it is. Okay. So only 4 different things. So I'm expecting you to know a little bit about this embedded technique where constraints are substituted inside of the equation of motion. Is not very important topic. Is ranked to be medium importance. Medium importance. Then really the main body of second midterm exam is about hydraulics. How to model the hydraulics. You see that each of the items, well, not each of the items, but the big picture of the hydraulics is ranked as a 5 stars. So that's as many stars you can get. So it cannot get any higher than that. So that's extremely important subject matter. Deformable bodies, not so important because it's only 2 stars. And again, if you are in a hurry, skip it. Then this real-time simulation, the different processes is ranked to be 5 stars, but it's based on the common sense. So I don't think that you need to invest that much about that final topic. But the one that is extremely important is, again, hydraulics. And hydraulics can be broke down to matters that are listed here. Properties of fluids, land fluid theory, flow types, modeling of hydraulic components. Each of these subcategories are ranked as well. How is they ranking? That you're going to learn momentarily. So that's a situation where we are at. Okay, remember this. This is extremely important to keep in mind. I know that some of you, I heard, or we suspect, based on the participation of these guided tutorials, that many of you guys are planning to skip the simulation work. I don't know if that's really the case. You can do that. That's okay. That's not a big problem. But make sure that whatever is your plan, game plan, or whatever is your plan you are thinking that you will follow, you will score at least at 35%. And again, if you see that things are going south, they are not going the way you plan, let me and Suresh to know that in advance. So you're facing some serious difficulties, let us know in advance. Once there is a deadline about the simulation work and you get back to us after the deadline, nothing, absolutely nothing whatsoever we can do for you. So we just cannot help. Why? Because this is going to be never-ending story if we're going to say you that you can get back to us whatever you want. So then there will be somebody coming back to us in the summertime and say, hey, now I'm ready to do my simulation assignment. That's going to be too much work for us. And we would like to follow something that is called minimum energy principle, very known principle in the mechanics. So we too wanted to follow that in our teaching. So, okay, so keep this in your mind. And in class quizzes, Mustafa just mentioned to me that I haven't emailed some of the results to him, and he is the one that is collecting them. We'll do that today. So you will see how well you're scoring in-class quizzes. So that information will be not momentarily, within let's say within this week available. So then you know. And you can get written exam in-class quizzes that in best possible scenario take you this, so this plus this is going to be 45%. Yeah, unfortunately, the grade will be still 1. But you pass. You can put this in you can forget about the whole class, so you don't need to worry about that anymore. And midterm exams. So as I mentioned, the week 51 is not a good week. That's a Christmas week, and no one wanted to work in the Christmas week, or let's say the end of the Christmas week when there's a New Year, Christmas Eve. Yeah, it's not a good idea to work then. So what I'm proposing here is that we will have an exam open 2 weeks' time, 2 attempts. Highest will be accounted. Exactly the same story than in the first midterm exam. And the weeks that it is open is 29th and 50th. 29th is Monday, December 5th. That's when the exam will be open. And it will be closed on, I need to check that from the calendar. So I said that it will be open on Monday, December 5th at 001. And it will be closed on December 18th, which is a Sunday, at midnight. I guess a couple minutes, 1 minute before the midnight. So 2 weeks' time, 2 attempts, highest will be accounted. Clear. Instructions and other practical details will be available in Moodle. So that's how we're going to go. And now, if you want to make your life miserable, if you are one of those people that want to torture yourself, I know a great way to do that. And the great way to do that is by participating in the written exam. First opportunity will be 21st of December, but don't do it, please. Because that would mean that the physical paper comes to my office, and I need to read your handwriting, and that's going to be making me feel angry. And when I feel angry, I'm going to give you no mercy whatsoever. Okay. All right, so that's about it. Embedded technique, let's take a look at that. And Yeah, so any comments, anything about these practical matters? Is everything clear? Everything is clear. Okay, embedded technique. Remember, this is about where you're getting a minimum number of variables to create your equation of motion. So it was based on this observation that when you use a concept of virtual work, in general case, you cannot set this equation to be equal to zero. You cannot, because virtual displacement might violate against the constraint. So what you want to do then is that you wanted to express this virtual displacement in a way that is not violating against the constraint. How you can make it happen? Well, you can make it happen by categorizing your general coordinates to independent generalized coordinates and dependent generalized coordinates. You can, generally speaking, you can do as you want, but in real computing, it's based on Gaussian elimination with a full pivoting. Okay, let me see. There is a. Okay, so is it possible to see in Moodle how is that you're doing so far? Huh. Can't you see that already? Can't you see how is that you're doing in weekly assignments? You can see how you're doing in the weekly assignments. You can see how you did in the first midterm exam. You haven't submitted the week simulation work yet, so you don't know how well you do. And then in-class quizzes, like I promised, will be available later this week. Okay, how you can see how you're doing in weekly assignments? So you go to model, you select the grading, crates, not grading, but crates. And that's the way to see it. Okay, take a look. Take a look. So if you are also following this principle of minimum energy, which may be your case, then maybe you want to skip some of the activities. I don't recommend you to do that, but up to you. Okay. All right. So I was here. So I was about to say that we wanted to express this in a way that is kinematically admissible. And we can do that by categorizing or selecting independent coordinates and expressing displacement based on the independent coordinates. And if we're going to do that using constraints, then it's automatically guaranteed that we do not violate against the constraint. That is then based on this coordinate partitioning. And this is the critical thing. Displacement, virtual displacement of all the coordinates and independent coordinates. This relation came from constraints. Jacobian matrix to be more specific. Okay. And then you can get equation of motion. There is a certain notations you need to use. And once you have here, then you have an equation of motion which offers you equal amount of differential equation than the number of degrees of freedom. Memorize this. That's important to remember. Okay, so that's about embedded technique. Hydraulics. And in the hydraulics, we have, what is it? 4 different subcategories. And they are the properties of fluids, land fluid theory, flow types, modeling of components. Fluid properties, 2 things that are important. One is very important, another one less important. One that is very important is a bulk modulus. Bulk modulus is the one that is equal, or let's say that they have is kind of the same than elastic modulus used in a strength of materials. It's the one that is defining how flexible is your hydraulics. And bulk modulus is something that there is something called effective bulk modulus that is taking everything that accounts the flexibility into account. That is fluid, dissolved air, how much air is involved to your system. Hard to know in real life, but you can make an estimate. Flexibility of components. Hose is the one that can lower the effective bulk modulus fairly significantly. So if you wanted to make your hydraulics to perform better, reduce the hose lines, use steel pipes instead of the hose lines. Could be the one solution to do so. Viscosity is another property, and the viscosity is only important in laminar flows. Laminar flow takes a place when we have a small pressure difference, generally speaking. That's not usually the case in mobile machinery. Okay, all right. Here's more information about effective bulk modulus and how you can derive that. So that's something that is very important to keep in mind. I would say that for sure the question bank for each of you will select the question related to bulk modulus and how it can be used. Something related to that. There's no, by the way, if I remember correctly, there's nothing that you need to compute, but you need to understand the concepts. So it's all about this multiple choices, and you need to select the one you feel that is correct. Okay, lump fluid theory. What is this lump fluid theory? That is a foundation of the hydraulic modeling. This is the way we can compute the pressures as a function of time. So what we do here is that we are discretizing our hydraulic circuit within the volumes where we are assuming pressure to be equally distributed. Once we have this discretized hydraulic circuit, then each of these pieces of hydraulic circuit can be computed by using first order differential equation. That's how it goes. And the flow that travels between these different volumes tries to equalize the pressure difference. That's how the hydraulics performs. And here is your first order differential equation. Look at the components here. So the first one is here, this one here, which is effective bulk modulus. Volume size, flow rate in, flow rate out, and then the component that describes the change of the volume. So that's the first order differential equation, very important. So if I would take a look at each of these are ranked 5 stars. Flow types. So 2 different flow types, laminar flow and third plane flow. In laminar flow and the pressure difference are linearly related, whereas in a third plane flow, they are quadratically related. So that's good to keep in mind. Okay, modeling of valves and other components. Well, the valve modeling, there are 2 steps. First, to model moving component, if there is a one, like typically there is a one, to know where the moving component is at any given time, and then the flow rate through the component. So those are the 2 steps. Simple, very simple valve, like throttle valve, there is no moving component. So you don't need to worry about something that is moving there. And we're going to use a method that is called semi-empirical modeling approach. It has a components from analytical approach and component from measurements. And how we do it is that we get started from these analytical expressions, and we can manipulate those in a way that unknown parameters can be obtained from measurements that are carried out by manufacturers. So you don't need to carry out the measurements because somebody did that already. You just need to find those unknown parameters from the measurements that is already available. So that's how it goes. Okay, then the direction valve, again, 2 steps. First, spool position. Very often there is a question that what is that this equation, this delay equation is representing. That's a spool position. And this one here is a time constant, like how fast spool can move from one location to another. Once you know the spool position, then you can model the flow rate through your component, like this. Okay, that's how it goes. Then the pump, you learn to model fixed volume pump and variable volume pump. We also discussed about modeling of cylinder. In a cylinder, only the problematic thing is related to friction. how to describe the friction. And remember, there is this stick slip friction you can see quite often. That's something that takes place in a hydraulic cylinder as well. Deformable bodies, there were two methods, the lamp mass approach and the floating frame reference formulation, conceptually very different because lamp mass approach is using theory based on rigid bodies, whereas the floating frame reference formulation is changing the kinematics. And because you're changing the kinematics, everything needs to be changed accordingly. Everything needs to be changed. Okay, let me see if I have any more slides. And then this real-time simulation, that's different product processes where the real-time simulation can be used. Common sense, more or less. Okay, so we're approaching the end of the course. So what was it? 3 weeks back, there was this, let me see what else I have here. Oh, I have this one. Hopefully I see you in a simulation laboratory course. There is an email regarding to that I received earlier today, and it was about how is it teaching. Teaching will be same than in this class, so it's a hybrid. So there are lectures that are delivered in a lecture halls, rooms like this, but because I'm an advocate of YouTube, I'm going to stream my lectures using a YouTube as well. Then about this simulation assignment, this is something that I need to ask from Suraj, how is that he's planning to do that. But basically, you can, if you're busy, you need to be someplace else, like someplace warmer than Finland, then you can do it. I think you can do it. I'm not sure about these guided tutorials, but lectures for sure you can go whatever place you want, but you need to have an internet connection. Okay, remember this is what happened 3 weeks ago. So you scored 100%, and look at my face. It tells quite a bit about what happened. So this is a screenshot from YouTube. So you made it. It is a big surprise. It was a big surprise. I don't think that it's not common at all. I think that there was some kind of like one visiting lecture that I delivered a while ago, and that particular lecture, people scored 100%. But like last year, it wasn't the case. That never ever happened. And I couldn't believe my eyes. Well, you can tell from my face that I couldn't believe my eyes because the question I asked wasn't even a very easy one. Because remember, there have been those easy cases like, what is that equation? Some symbol equation is representing. And then there is these options about rotational particle and other nonsense. And you guys never scored 100%. So it was a big surprise. And I made a promise that if you guys score 100%, then I will be happy. I promise that I will do something unusual, which I never do because I'm stiff, not artistic guy and everything. So here's my promise then. So what do you think is going to happen? I don't even know by myself. Okay. All right. So then this happened just before the COVID time. I made a visit to Korea. So it's me. So okay, this story is a long story. And I was having the dinner with my friend, Professor Choi, and after the dinner there was this place was in some kind of complex. There was a restaurant and then a theater, big one. And then after the dinner we went to see some kind of traditional performance, Korean performance. A lady is dancing, and that was a kind of like weird thing because every now and then they went to the audience and asked somebody to hold the stick or something, like interaction. The one that I try to do with you guys all the time. And then came big surprise. I was somewhere in the back, of course, and then they finally came and pointed me in their finger and they said, "You need to walk with me and come to the podium." And I walked with them to the podium, and this is me, of course, and these ladies that are a little bit shorter than I am, and then they are beautiful ladies, of course, and when comparing these beautiful ladies against me, the difference is enormous. So you can easily recognize me. And then they started to put this costume on it, and the costume is like this. So there is a dress, and it's getting even worse than that. This one, and then what? Okay. Okay, the music is not on. Okay, so guess who is me? Okay, I can tell you is I'm in the middle. So I'm sure you did not recognize me, but I'm the one in the middle, and it continues here. This is the same. So I want to go. Oh, look at this. So now you don't know. And one more thing. This is what we saw already. Okay, one more. And what the thing that you don't hear all the time that my family and my friend, I thought my friend, is laughing so loud that it's hard to even hear the music because they had so much fun. So that's about it. Thank you very much. All right. Hope to see you then in January. All right, guys. So this was it. Thank you very much. It was a lot of fun. Is this going to be where? This is going to be a part of the class. I mean, because this went to the YouTube, so you can see that later. But keep this YouTube channel to be our private information. All right. Thank you very much. And thank you for online participants too. So all the best. All the best, and see you guys later. And for Jedi student, my heart belongs to you, and I know that it's hard and everything, but don't give up. Okay, so I'm gonna close this where it takes me. Oh, thank you very much for those comments. And I'm gonna close it.